Our presentation by Arun Kumar, USA number 3BR59A166 from Mechanical Engineering Department of BITM College. A seminar on performance analysis of valveless micropump with disposable chamber actuated through amplified piezo actuator for biomedical application under the guidance of Surya Vasant Yadahalli sir and HOD of Mechanical Department Dr. Edvaldi Basavaraj sir. Here comes the contents. Introduction, concept, fabrication, table, setup, optical performance, advantages, conclusion, references. Introduction part. The development of miniaturized device has gained significant attention over the past few decades, particularly in the field of microfluidics. The growth of submillimeter and microscale engineering and precision fabrication technologies has made researchers realize the miniaturized device development to micro nanoscale. The development of miniaturized pumping systems has also been the topic of research, particularly for microfluidic applications to handle or deliver a precise volume of the fluids at the required rate and pressure. Miniaturized pumps or micropumps possess advantageous features such as faster response, compactness, portability, lower energy requirement, and the use of cheap or cost effective material. Micropumps as a device find application in biomedical, electronical, cooling, automobile, aerospace, and fuel cells, environmental monitoring, etc. Here comes the concept for disposable chamber micropump. The conventional micropump has piezo actuator bonded onto the oscillating diaphragm, but disposable micropump requires the pump chamber without bonding between the diaphragm and the actuator. The functioning of disposable chamber micropump with the piezo actuator follows the sequence of supply and pumping mode. The diaphragm flexes in a particular direction due to the force exerted by the actuator, resulting in the increased pressure inside the pump chamber. Thus, the fluid gets pushed out of the chamber, which implies the pumping mode. The regain of the initial position of the diaphragm causes pressure drops inside the chamber. This pressure drop leads to flow of the fluid inside the micropump chamber. This sequence of supply and pumping mode continues, leading to the pulsating flow from the micropump. The diffuser at the inlet and outlet provides the necessary rectification of the fluid and converts non-directional flow into the directional flow. The actuator of the conventional piezo micropump must take care of the raising and lowering of the diaphragm during the pumping and supply process due to the permanent bonding between the actuator and diaphragm. Since the disposable micropump do not have bonding between the actuator and diaphragm, the elastic force brings the diaphragm back its equilibrium position. Thus, the diaphragm of disposable micropump should possess sufficient resilience, else the diaphragm may experience upward impact before it comes to the equilibrium position, leading to reduced stroke volume. The diaphragm design is an essential aspect of the efficient working of disposable micropumps. Here comes the diagram. Figure A, which it consists of before actuation. Figure B is of about pumping mode. Figure C is about diaphragm restoration, and figure D is about supply mode. Fabrication of the micropump. The proposed micropump was fabricated from PMMA, polymethyl methacrylate, machined through a conventional CNC machine. The micropump has different structural layers assembled one over the other. The bottom supporting structure along with the actuation mechanism was machined through the traditional CNC milling machine. The disposable chamber consists of a flexible boss diaphragm, a pump chamber, and the flow rectification mechanism bonded together to form a single component. Conventionally mounted silicon rubber sheets constituted the boss diaphragm for proposed micropump. A PMMA mold machined through conventional CNC milling was used to pour the liquid silicon rubber with curing agents and allowed to undergo room temperature curing represents the process followed in the silicon rubber diaphragm fabrication. The pump chamber and the nozzle diffusers were also fabricated from PMMA by using carbon dioxide laser cutting. Brass tubes on the nozzle diffusers acted as inlet or outlet, which were connected to inlet and outlet reservoirs respectively. Here comes the diagram, and figure 1, which it shows weight and mix of silicon rubber and curing agent. Figure 2, which it consists of remove air bubbles through vacuum chamber. Figure 3 is of about pour into the mold, and figure 4, which it consists of room temperature curing, and figure 5, which it consists of silicon rubber diaphragm. And this diagram, which it shows how the process is made. boss diaphragm, disposable part, chamber with nozzle or diffuser, micropump assembly of about 10 mm, bottom support, reusable part, actuation mechanism. Here comes the table. Specification of the Bose diaphragm, micropump, chamber and the nozzle or diffuser implemented in the micropump. Specification of the Bose diaphragm. The material which it is used is silicon rubber. Young's modulus is of about 1.15 megapascal, density 1070 kg per meter cube, Poisson's ratio of about 0.47, effective chamber of 30 mm, thickness of about 0.2 mm, chamber parameter, diameter of the pump chamber of about 30 mm, depth of the pump chamber is about 7.5, 0.75, 1.00, 1.25, 1.50, 1.75, 2.0. Inner diameter of the inlet or outlet tube is about 1.60 mm. Outer diameter of the inlet or outlet tube 3.3 mm. Nozzle or diffuser parameter. Length of the channel 2.50. Width of the inlet 0.50. Width of the outlet 0.94. Angle of divergence 10 degrees. The setup for experimental measurement of micropump performance. A sinusoidal signal generated from a function generator drives the actuator APA120S with the amplitude of 10 volts to 150 volts and frequency of less than 20 Hz. A linear amplifier voltage amplifies the sinusoidal signal from the function generator. The optimized diaphragm parameters are fixed based on the measurement of diaphragm deflection through laser displacement sensors. The micropump performance assessment involves measuring the mass flow rate of the pumping fluid for a different range of frequencies and voltage values of the actuation signal and converting the mass flow rate into the volume flow rate. The experimental measurements have been carried out under ambient room temperature of about 27 degrees centigrade with water, blood plasma, and whole blood mimicking fluids. The measurement of the flow rate adopted similar approach as followed by H. Asadi Dershki. The flow characterization involved the collection of pumped fluid in the measuring jar and measurement of the mass of fluid accumulated for a preset time through precision weighing scale. The five number of trials were performed and the mean value of the flow rate with corresponding standard deviation was considered for experimental measurements to justify the reliability of the experimental data. The levels of reservoirs were adjusted such that the liquid level in the inlet reservoir matches with the outlet reservoir level. This prevents the self-generated flow due to the siphoning effect. Thus, the micropump pumps fluid only when the actuation signals are applied to the actuator. The pressure characteristics measurement of the proposed micropump consider the difference between the height between the inlet and outlet reservoir. The height of the outlet reservoir was varied until the flow rate reaches 0, which corresponds to the blocking pressure of the micropump. The measurement of flow and pressure characteristics of the blood plasma and blood mimicking fluid followed the same above approach. And here comes the diagram. Computer with oscilloscope, function generator, voltage amplifier, actuation and data acquisition, diaphragm reflection, deflection measurement, communication module, laser displacement sensor, and flow and measurement, pressure measurement, precision weighing scale, inlet reservoir, micropump, outlet reservoir, pressure head. Laser displacement sensor is used. Bose diaphragm, computer with oscilloscope and laser sensor, data recorder, communication module, function generator, laser displacement sensor, amplifier, Bose diaphragm with actuation, and amplifier set rate LC75A 50 mm. Optimal performance parameters of the proposed micropump. The experimental approach adopted for the proposed micropump designed focused not only achieving the higher pumping rate but also on having a robust disposable design that could involve multiple biomedical applications. The proposed micropump delivers the optimal performance with the diaphragm thickness of 0.2 mm, the Bose ratio of 1.33 and the chamber depth of 1.25 mm. Here, this represents the variation of the volume of fluid pumped per stroke of the diaphragm, which signals pumping resolution of the micropump. The flow rate can be modeled between 10 volts to 150 volts at 5 Hz, indicating the suitability of application in the low frequency range. X-axis is of about voltage and Y-axis is of about average flow or stroke. This represents the optimal performance parameter of the proposed micropump of fluid category of water, blood plasma mimicking fluid, blood mimicking fluid. This represents the comparison of performance and design parameters of the proposed micropump with recently reported micropump by various researchers with water as a working fluid. As observed from the figure, flow rate achieved with the proposed design outperformed some of the micropump reported in recent years. Though the micropump proposed in the present study occupies larger volume due to the reusable actual part, the flow rate per unit cross-sectional area of the chamber is superior to the most of the micropump. And here comes the graph part. Minimum flow rate per cross-sectional area of the chamber. Advantages: it is simple in design, freedom from fatigue failures, flow rate developed. The optimized design of micropump is capable of delivering a flow rate of 300 ml per hour to 432 ml per hour. Here comes the conclusion part. The proposed micropump involved low-cost polymeric materials such as polymethyl methacrylate, silicone, rubber fabricated through conventional CNC milling, laser cutting, and molding processes. The lower value of the chamber depth influenced the returning of the diaphragm during the suction stroke due to the enhanced effect of the adhesive force, which degraded the flow performance. The higher value of chamber depth results in a lower compression of the fluid, which brings about raised pumping rate. The optimal value of chamber depth was found to be 1.25 mm, which delivers the maximum pumping rate. Increase in the fluid viscosity also led to a reduction in the pumping rate due to the increase of the adhesive force on the diaphragm. The maximum flow rate of water, fluid mimicking blood plasma, and whole blood was established to be 7.192 ml per minute, 5.013 ml per minute respectively. Consideration of the performance parameters coupled with the advantage of the disposable chamber, the proposed micropump can be well established for biomedical application with the integration of appropriate control systems. And here comes the reference part. Thank you.